Welcome to section 1.0, Rates of Change. To get us started, let's look at example 1. After t hours, the population of a bacteria colony is modeled by p equals f of t equals 35 e to the 0.5 t. When does the population grow faster? During the first 3 hours or between 3 and 4 hours? Okay, let's look at this example and let's look at the graph first over here on the right to get a feeling for what's going on. So the graph shows how fast our bacteria colony is growing. We can see that at t equals 0, the population number is shown by the vertical intercept over here. That looks like it's a little bit below 50. So maybe 40 or something like that. And then we can also see that our population, as time goes on, our population is growing. And the question in this problem that we'd like to answer is it growing faster between t equals 0 and t equals 3? Or between t equals 3 and t equals 4? That's the question. So to figure that out, let's look at what the population numbers are at those times. So we already estimated at t equals 0, it's a little below 50, around 40. At t equals 3, we can also go up to the graph and see that the population of bacteria is about 150, a little bit bigger. And at t equals 4, it's about 250, 260 over here. So looking at those numbers, when did the population grow faster? That's not that easy to answer. We can see that between t equals 0 and t equals 3, it looks like the population grew more by a bigger number, but does that mean that it grew faster? Or did it grow faster between t equals 3 and t equals 4? Let's see. So how much? Let's start by asking how much did the population grow? And so between t equals 0 and t equals 3, so that's during the first 3 hours, the change in population, we actually have a symbol for that. We call that delta p. So this is the change in population. We can compute that by finding the population at time t equals 3 denoted by f of 3, or function when we plug in t equals 3 minus our population at t equals 1 denoted by f of 1. And we can compute these. We could estimate them from the graph, but we also have a formula for our population, and so we're going to use that instead to get a little bit of a more accurate number. So f of 3 is 35 times e to the 0.5 times 3. We are substituting 3 in for t in our formula. And then we are subtracting f of 0. I said 1, but really we want f of 0. So we are subtracting 35 times e to the 0.5 times 0. We can estimate these numbers. We can plug them into our calculator to get about 157 for f of 3 and 35 for f of 0. And so we can answer the question, how much did the population grow? It grew by 122 bacteria. During the time from t equals 0 to t equals 3, so during the first 3 hours. What about during the second time interval? So during the second time interval from t equals 3 to t equals 4, we can also compute our change in population, and that is similarly f of 4 minus f of 3. Substituting those numbers into our formula, we have 35 e to the 0.5 times 4 minus 35 times e to the 0.5 times 3, 0.5 times 3, and that is approximately 259 again using the calculator, minus 157, and that is a total of 102 bacteria. So at this point we can say, well, during the first 3 hours of our population grew more because it had 122 additional bacteria. During the time from 3 to 4 we only got 102 additional bacteria. But that wasn't our original question. Our original question was, when did the population grow faster? And so faster takes into account also how long it took the bacteria population to increase by the amount that it did. And during the first 3 hours, we have a growth of 122 bacteria, but it took 3 full hours to get that, whereas the 102 bacteria increase happened just over 1 hour. So we are computing something called the growth rate that takes time into account. So we want to compute the change in population, but then we want to account for how long did it take to get that change. And so we are taking the change in population and divide by the change in time. So for our first population from t equals 0 to t equals 3, we get 122 bacteria over a time interval of 3 hours. That is 40.6 bacteria per hour. To get 122 in 3 hours, the bacteria would have to grow by 40.3 bacteria per hour on average for each of those 3 hours. What about the other time periods? There we had delta P over delta T from t equals 3 to t equals 4 is 102 bacteria divided by just 1 hour. That is a growth rate of 102 bacteria per hour. And so when it comes to growth rate, we can see this is much faster. So this is a faster growth. Much faster. Graphically, we can also see that by drawing in lines whose slope represent these growth rates. So when we're looking at those two growth rates, for the first 3 hours, we had a change in population that is denoted by this right here. This is our change in population, and then here we have our change in time. This fraction of delta P over delta T is the slope of the line connecting the first 2 points right here. Let's call that S1. That's slope 1, and that slope is 40.6 bacteria per hour. And for our second time interval, we're getting a similar representation. We also have a line where we have delta P over delta T for our second time interval, and that, let's call that S2, and that was 102. So we can see that the slope of the second line is much steeper than the slope of the first line, and so note that the slopes of the lines S1 and S2 are the two growth rates.